Okay, here's a quick solution of this classic problem that we've been looking into here in Chapter 7 for sampling. And again, you have to think in terms of a big process that we don't know the entire population, and we're taking a sample, and we're taking advantage of some rules and relationships here that let us come up with some answers when we do some sampling to figure out what the likelihood is of how far away our sample is from actuals of the population. Okay, so this problem here comes in as 7.18 in the book, but it's chapter, or rather question 5 in our homeworks here. So the video game satisfaction rating case, I'm going to paraphrase here, and they're saying that we suspect that, or we're happy with the fact when we have a customer satisfaction rating of 42, okay, customer satisfaction rating greater to or equal than 42, we're taking 65 samples, so n is equal to 65. What other information do they give us here? Okay, so they also tell us that we take a sample and we find out that our sample mean is 42.95. So you should start thinking immediately, this is an appropriate, acceptable mean, and this is actually what we observe. But we don't know this. Okay, all we're saying is we'd like to make sure that our customer satisfaction is 42, or we drew some conclusion before that that there is an average of 42 customer satisfaction rating, and we just did a sample and we got 42.95, so we're 0.95 above this. And think about that in terms of one rating point. You're basically one rating a point above this potential population mean. Okay, and through practice, it tells us that through practice that the standard deviation of the population is 2.64. And one of the reasons that we can go ahead with this is quite often in processes, the thing that changes between samples is not the spread or shape of the sample mean, but it shifts. It doesn't scale. Scaling would be is if it started stretching like this. Notice here we're limited here. Here, look how far out we are here. What normally happens is that you're just going to get a shift where the sample mean is a little bit different. Dot, 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 down here. Okay. So when we do a random sample, it's just based on the samples that we put our hands on or took into the computer here. And every time we sample, we're necessarily or likely going to get a different mean here because it's the probability or the statistics of the sampling process here. Okay, so anyway, that's why if we know 2.64 is the spread or the standard deviation, remember the average distance to the mean of all the points, right? So if that stays constant and we only have a shift, that's why in these problems we're able to accept the fact that, through experience, we think that our population standard deviation is 2.64. How do we adjust for that? Well, we have the relationship here where the spread of the sample mean is equal to that of the population over the square root of the number of observations, which was 65 up here. So let's do some calculations here. This is pretty much straightforward solution. Okay, so let's see, what can we calculate? We could do it all in one, or I can make this as a partial solution here. So what's the first thing we're going to do? Let's go after that standard deviation of our sample mean. So that's going to be equal to 2.64 over the square root of 65. Okay, and see how small that is? That's always going to be smaller than the standard deviation of the raw data. This is the population data, raw data, and then we take a sample. Standard deviation of the means, remember what we're doing here, there's a bunch of means. We have a bunch of samples that come in, all right? And every time we take a sample, we take 65 readings. Okay, so that's how that works. So we get a standard deviation of 0.3274, et cetera, et cetera. Okay, and now they want to know, consider the sampling distribution for random samples of 65 customer satisfaction ratings that we already talked about. Use the properties of this sampling distribution to find the probability of observing a sample mean greater than or equal to 42.95 when we assume that mu of the population is equal to 42. So we're going to go straight forward. This is straight up z transform. I'm sorry, z score here. And we take our point of interest, how far away from it from the mean. In this case, see, what we'd be using is the sample mean, but we know that we can use, since the count is 65 greater than 30, that we can treat the sample mean as a normally distributed function here. Okay, so we can use the population mean. Okay, so we're going to stick that in there, and then we calculated our standard deviation of the sample mean here as to 0.3274. Okay, so we did that ahead of time, kind of knew what was going to go on here. So if we put this in the equation, what are we going to get? So we're going to look up z here, try to get z, and z is equal to 42.95 minus the mean, and we're going to put that in brackets because we're going to divide by standard deviation. I need to finish off my brackets there. Okay, so if you think about it, we were 0.95 away from 42, the mean, with our point of interest, 42.95, 0.95. Our standard deviation is 0.32. How many times does 0.32 go into that 95? Roughly 3, just shy of 3. We're almost 3 sigma out from the mean, okay? So the probability of getting a sample above 42.95, right, is going to, what do we do with this? So now this is our z-score. So if we go into the table, remember what we're being asked versus what we can get out of the table. Out of the table, what we do is, here's our normally distributed data. There's that 42 sample mean. We're up here at 42.95. Okay, something tells us that these numbers are pretty clustered around 42 average, right? We're almost 3 standard deviations out up here, right? In an empirical sense, we know that at 3 standard deviations, we are up there at 99 point something like 73. Okay, so what we're going to do is, when we go to the table, is we're going to get all this area under the curve up to 42.95. The equivalent in standard deviations is 0.32 right there. Our z-score is 2.9. Go into the table, but we're just going to use this to calculate. I want you to really use Excel for this. Norm.s.dist of this number. Now it's positive. We're above the mean, okay? And we want cumulative, all right? So I put a 1 in there, okay? But what we're being asked is, what's the probability of getting 42.95 and above? So we want 1 minus that number, the other part of the curve. And just for grins, what we're going to do is, I'm going to say that is equal to this and just turn it into percentage, or format it as a percentage. Just formatting here, not truncating any data off here. Percentage. Okay. All right. So 0.9%, 0.19% of the curve is above 42.95. That's because we're 3 sigma out. So remember, the tails get really thin up there. After 3, it gets pretty quiet. There's not much going on up there. Okay. So the first, let's see how we did. Okay. Okay, so let me move this out of the way. Boom. Here. See what we got here. See how they answered it, right? So they repeat the information. Our mean was 42. The standard deviation of the population was 2.64 from experience. We just assume one way or another we're above 30 samples, so it doesn't matter what the underlying nature of this, what kind of distribution we have underneath the covers here of the raw data, because we're above the n is equal to 30 mark. So we can assume that we can treat it, the sample mean, as normally distributed there. Okay, so we can just drop the u down here and use that as our mean for the sample mean, okay? And then we calculated, okay, we did that right. We got our standard deviation of the sample mean to be 0.3275. That's what we got over here. And then the probability that x is above 42.95 is 0.0019, which we got. Okay, so that worked. Good for us. Okay. So the second part of this question, if u is equal to 42, what percentage of all possible sample means are greater than or equal to 42.95? We already answered that. Since we have actually observed a sample mean of 42.95, now remember that number is 3 sigma up from our implied mean of the population at 42, is it more reasonable to believe that one, u equals 42 and we have observed a sample mean that is greater than or equal to 42.95 when u equals 42, or 2, that we have observed a sample mean that is greater than or equal to 42.95 because mu is greater than 42? Okay? So the way that we answer that is we have a very low probability of anything happening above 42.95, okay? It's very unlikely, this is saying that it's very unlikely that the mean of the population is actually 42. As in the long intro video that I did toward the end when I was going over the problems, this is a mystery that we made an assumption about. We're not really sure what the population mean is. And when we went and we sampled and we got 42.95 based on other things we knew, most especially that we had this magically prepared number of 2.64 as the population standard deviation. That's a gift. Think about how you would actually get that. We don't know the mean. Why would we know the standard deviation of this process? Well, this is where it comes into expertise, is that people have used their expertise to say that they're pretty sure that, speaking of statistics and probability, they're probably that we can apply the 2.64 from other experience we have to this. Because to get the sigma, don't forget, of the population, we have to have the population mean to calculate this. So if you notice, there's a little bit of trickery going on here. I want to make sure you're aware of what's going on in the problem. They're sort of giving us some information here. In industry, somebody came in and said, oh, you know what, just use the 2.64 as the population standard deviation. That's what we've been running for the last 15 years or so, okay? So we take the sample, and we ended up, this one sample we've got, it's very unlikely that the population mean is 42. Because the sample set that we took was 3 sigma above it. It's more likely that this is not correct and that we can shift this whole, the idea of this entire sample mean up to the right. The mean is probably not 42. What we're saying is if we take a few stabs at this and we said, what if it is 42 point, and what's our standard deviation here? 0.33, okay? So what if we guess that the population mean is 42.33. See, we're coming in to the 42.95. If we rerun all our numbers, okay, what we're going to find is that here's our stake in the ground, 42.95. And at first we thought there was a spread like this. And what it says is we keep this stake in the ground is where this is where our sample mean is, but we're going to get a tighter fit here. Okay, because what we're doing is in theory, or in practice actually, is we said 42 was too low. It's very unlikely that we picked, when we did a sample, that it really would be that far away from the mean. So let's say it's 42.33, right? And I'm using 0.33 because that's the standard deviation. Just shift it up by 1, and we have to start making this narrower and taller as to what our imagined population data really looks like. Okay, this is a key concept moving forward because this is going to lead to our confidence intervals in our hypothesis testing. Okay, because our hypothesis is going to be, does that seem right? That's what they're asking us in this problem here, is does that seem right that our samples, we might have taken 10 samples of 65 readings each, and the mean of those samples was 62.95. Does it make sense after we took all this data that it would be that far away from the population mean? So in effect, we're beginning to reverse the process here. I'm trying to help you out with that, is how to look at this. We're using this normal distribution in a new way, where the known used to be like the mean was 42, but now because we're sampling, we don't know what the mean of the population is, and we're using the sample mean to start saying it's probably not 42. It's probably 42.33 or maybe even 42.66. And this is the reason I'm going over this in such detail is this is the core to getting into confidence intervals and hypothesis testing, this concept. So this was problem 5 in the homework, the 5th problem. You can see question 5 of 9, but it happens to be exercise 7.18. That's for my own reference. Hope that helps.